opened up for theoretical physics yet.
Right. I'm trying to think if I should bother with it. So how long is the how does it go? This thing, is it it's an hour or 50 minutes or
Yeah.
Yeah,
so if the talk is 40, 50 minutes, and then we have questions after.
Okay.
Well, I mean, it's quite flexible, but something around that time would work.
Okay. And is there a way that I can test whether I'm sharing the screen properly?
Yeah, you can try sharing the screen now and we can see if it works.
Okay. Drop this. Because it's strange with presentations, because it's somehow, I think if I do this, let's see if this works. I know it sometimes goes weird. Share. What do you, and then if I go slideshow. Okay, you see my, you're seeing the wrong thing. Can you see the slide, or do you actually see my full overview?
You can see the full overview right now.
Okay, so I don't know how to stop sharing this down now. Share screen. And let's see if this does it. Does that do it properly?
Yeah, that's working.
Okay,
well.
Great. Okay.
If you can just wait 1 or 2 more minutes just in case there's more people joining, then we can make a start.
Great. And so there will be there'll be some sort of a chat. This is not the best way to do this, actually. I wonder if I can make this. I guess, is there a way? Because the problem now is I can just see my presentation, but I can't see the Zoom part of it. But maybe what I'll do is, can I log in from maybe my phone or something, so that I have my phone? Let's see if that works.
The Zoom part will have the Q&A, but I can read the questions out.
Okay, so I'm connecting now with my other account. So there we go. And now, if I mute it, how's that? Your microphone is unmuted. I don't want to do that. How's that? No. Mute. There we go. So if I go there, okay, so I can see the Q&A there.
Yeah.
And I should be able, and if I go onto the red, no, leave webinar. Okay, I guess I won't be able to see much, but maybe, I think I can see the full participant list. now, but I can't get any feedback from that.
Yeah, I can read out the questions
Okay,
when we
great.
get to the part.
Okay. All right, that sounds good.
Okay. Yeah, I guess we can make a start there. Thank you everyone for coming to this talk. It's the second event of Quantum Information Society of the term, and we're very pleased to have Professor Jonathan Oppenheim to speak to us today, who is a professor at UCL and has done work in various areas of quantum information, including a lot of work in quantum thermodynamics. But today we'll be talking to us about post-quantum theory of classical gravity. So I'm really interested to hear this talk, and I hope everyone else is as well. And please put any questions you have in the Q&A section of the Zoom, and we will discuss questions at the end. So please put your questions there as we go through the talk. Yeah, so thank you for coming, Jonathan, and please start when you're ready.
Great. Thanks very much for the invitation. And yeah, please do ask lots of questions in the Q&A during the talk. I'm happy to kind of stop and start as we go. Let me now see if the screen shares properly again.
I think it's working well.
Great. Okay, so I'm probably not going to be talking a lot about the actual this post-quantum theory of classical gravity. I'll probably spend most of my time just talking about some very basic questions like, must we quantize gravity? And so I'll try and just talk about some of the, I guess, questions that are in the air and what kind of possible directions we can take. And I'll, if people are interested, there's an archive paper which has lots of details, but here I'll just talk about the motivation and just look at what sort of things are possible. And this is joint work with a few students of mine and some postdocs. So Joan Camps, Barbara Soda, Carlos Baracchieri, and Zach Weller-Davies. Okay. So there's probably some of this will be review, or a lot of it will be review. But you all know that I think that there's, well, these are three of my favorite mysteries in physics. The first is that gravity, Einstein's theory of general relativity, and quantum theory are somehow inconsistent. That's obviously one of the biggest open problems in modern physics. And then there's some other problems, paradoxes. So for example, number 2, sometimes called the measurement problem, sometimes called the reality problem. It's sometimes people don't consider it a problem. It's the question of how does the classical world emerge from the quantum world? And I'll touch on that. And then, of course, there's the black hole information problem, or the paradox, or the annoyance, whatever you want to call it. Some people think it's a paradox, some people merely an annoyance. I'm probably more towards the latter. So let's talk about those mysteries and why I think they're all related to each other. Okay, so the first is, as you all know, that gravity and quantum theory are inconsistent. And you can see it from Einstein's equations. So here's Einstein's equations. There's on the left, you have G mu nu. That's the Einstein tensor. So it encodes all the information about space-time. So the encodes the metric, the curvature of space and time. And it is, we treat it classically. So it represents the classical background that matter lives on. And then on the right-hand side, we have the stress energy tensor of matter, T mu nu, or T mu ni, as we should actually call it, as we should call it in Greece, in modern Greek. So T mu ni encodes it's the stress energy tensor, encodes the energy and momentum and stress of matter. And since matter is quantum, this thing on the right-hand side is an operator. And of course, it's not possible that we should have a C number, a number that's equal to an operator. So there's something wrong. This is inconsistent. And I suppose on a very fundamental, so almost universally, it's believed that we should make this consistent by quantizing gravity. That's the standard dogma. But I think there's a lot of conceptual issues which arise if we do try and quantize space-time. And that's essentially because it's the arena in which quantum theory happens. So, in quantum theory, you have on some initial Cauchy hypersurface, you define the quantum state, it evolves into the future, and quantum theory requires this causal structure to be there from the beginning, or the structure to be there from the beginning, I should say. And if we quantize it, then that's a bit strange, because in quantum theory we have this Schrödinger equation, we have a predefined time, and now if time itself, if what we call the past and the future is quantized, it becomes a little bit tricky to it becomes quite tricky to even know, whether we can do quantum theory. So I think it's worthwhile wondering whether we should actually quantize gravity. Okay. And I would say that space-time is fundamentally different to the matter which lives on that space-time. And a priori, there's not necessarily a reason why we must quantize it. So that's one mystery. And attempts to quantize gravity have so far, I would say, failed quite badly. And so we're already past the point of 100 years of failing to quantize gravity. So the second question, which you're, I'm sure, all familiar with, is just the question of how the classical world emerges from the quantum world. How do things become classical? And so another way of saying it is, why don't we see macroscopic superpositions? Why don't we see cats which are alive plus dead? There are people that would say that decoherence solves that problem. But I think most people would agree that it is an issue, and that we don't really at this point understand how the classical world emerges. And one thing I'm going to argue is that in order for the classical world to emerge, we actually need classical objects. So we can only have in some sense, within quantum theory, there's no such thing as a classical state. And it's only by having fundamentally classical objects that the classical world can emerge. Good. And the final thing I will mention is the black hole information paradox, or the black hole information annoyance, depending on your view. And let me just describe it quickly. We imagine that we have a black hole which is in a pure state, and we can throw matter, say dust. Well, we could collapse a pure state of dust into a black hole. We could throw some systems which are in a pure state into the black hole, and then we let it evaporate. And Hawking showed us that it should evaporate thermally, and at the end, when it's finally evaporated, it'll look purely thermal. And that seems to contradict quantum theory, where because we have a pure state which is evolving to a mixed state, and quantum theory is unitary. But it's not that hard, especially people in quantum information. We are always dealing with decoherence, and we know how to describe systems which undergo decoherence. So in that sense, it may be that allowing for information to be destroyed is not such a big deal. But if you believe that black hole, if you believe that nature is fundamentally unitary, that information can't be destroyed, then you really run into problems. And there's a stronger version of the black hole information problem, which is like a 2.0, due to Almeri, Merolf, Polchinski, and Sully, which actually uses some nice ideas from quantum information theory to really sharpen the paradox. And what you find effectively is that if you believe that information is preserved, then you either need to give up on something very sacred. You either need to give up the equivalence principle, or you need to give up low energy effective field theory. People in string theory are willing to give up even more, like their linearity or their dignity. If, on the other hand, you want to go for the horn on the right, and you want to believe that information is destroyed, then you might have to give up either locality or energy conservation. Maybe. It's less clear. And that's why I think if you are willing to jump on the horn on the right, then maybe it's the black hole information paradox is more of an annoyance. Now, almost everyone believes that we should jump on the horn on the left, but I think it's important to explore what the options are and what happens if you jump on the horn on the right, and that's something that I'm interested in doing. I'm not going to describe the black hole information version 2.0 too much, but I'm happy to take questions on it later if people want. So I'll pause there maybe and just check if there's questions, but those are the three mysteries that I claim may all be related in some way.
If anyone has any questions, you can pop them in the Q&A.
But otherwise, yeah, I can just go on. Yeah.
Yeah, happy to carry on.
Okay, good. So what we'll see is that there is, I think, a relationship between those three mysteries, or there could be. And so what I want to do is I want to first look at the first mystery and ask the question, do we need to quantize gravity? Is it possible that we can still treat space-time classically and have a consistent theory of space, time, and matter? Is that possible? And the way I would word it is, I don't personally know. My background is quantum information theory. I want to quantize everything that I see, and so I would like space-time to be quantum, or even weirder. And so it would disappoint me a little bit if space-time was classical. But I just want to ask the question, is it possible that space-time is classical? And what we'll see is, okay, obviously we have no idea whether it's classical or not, but what I will show is that it can be classical, that there is a consistent theory in which we can couple quantum matter, quantum fields, to a classical space-time. We can make it perfectly consistent. And then I want, well, I'll just have to claim this, and maybe you'll see a bit of it, but what it turns out that if you assume that space-time is classical, then what you find is, you can get a consistent theory, and also it would necessarily cause collapse of the wave function. So it would necessarily cause the classical world to emerge in superpositions to choose one element and collapse to that particular definite state. It would necessarily, having classical spacetime would necessarily lead to information destruction. And so if you believe that spacetime is fundamentally classical, then it would help resolve two other mysteries of physics that we have. On the other hand, I want to hedge my bets a bit, and I'll just say that if it's not fundamentally classical, then the theory I'm going to present here is a good effective theory. And we are often trying to understand things like black holes or cosmology in the early universe, where we want to treat space-time as being classical and let matter be quantum. And so this theory I will present, I'm not actually going to get much to the theory, but if I were to present the theory, you could regard it as fundamental, but you could also regard it as some effective theory, which I think is it's important to explore, because even if black holes don't fundamentally destroy information, they certainly, they appear to at low energy, and so the low energy effective theory we come up with should include information destruction in it. Okay, so the outline of what comes next, and I'll spend almost all my time on the first question. And it's the question of, can we couple quantum systems to classical systems in a consistent way? And then we would be interested in what is the general form of this kind of dynamics. And what I won't talk about is how to apply this to general relativity coupled to quantum field theory. But I will maybe just show a few of the kind of things you need to resolve. Good. So let's talk about the question, can we couple quantum and classical systems together? And what I will just talk a lot about is, I'll do a lot of coin flipping. So here's a coin, and I will have some planets because we were talking about gravity. So rather than electrons, I always have a big planet in mind. So we can think about this, for example, entangled state here, where we have with, amplitude 1/√2, we have, I think that's a head. Yeah, I think it's the Brexit coin. We have a head, and that's entangled with the planet on the, sorry, that if the head is if the coin is head, then the planet is on the left, and that's in a superposition with the coin being tails and the planet being on the right-hand side. And in this entangled state, if we were to look at the coin, it's in a statistical mixture of being heads and tails, and the planet is also in a statistical mixture of being on the left and the right. So we'll talk a lot about this kind of a state. And now I'm going to talk about this thought experiment, which is due, I think, initially to Feynman, but it's kind of been, there's different versions of it, and this may be a charitable version of what Feynman was thinking, because it's actually, you can read this, you can read the proceedings of the Chapel Hill conference. It's fascinating reading, and I do recommend it. And it's a bit unclear in modern language what to make of what Feynman is saying, but roughly, I think this is his thought experiment. And he relays this thought experiment to, in order to argue that we have to quantize gravity. And the thought experiment goes something like this. It's a double slit experiment. So we have two slits, and instead of sending an electron through both slits, we send a planet through both slits, maybe a large molecule, which has some mass to it. And now, depending on which slit the planet goes through, it'll create different it'll create a different gravitational field depending on which slit it goes through. And so what we do is we sit far away with a gravity wave detector, for example, and or maybe just a pendulum with a pendulum with a little weight, which we use to measure the gravitational field, and we try and determine which slit the planet goes through. Okay, if we can use the gravitational, so if each one has a different gravitational field, and the gravitational field is classical, we can determine which slit the particle went through, because, as I just said, if it went on the left or it went on the right, it will make a different gravitational field. Classical fields we can determine unambiguously exactly, we can measure it as accurately as we want. So we can measure the gravitational field to arbitrary accuracy because it's classical here. And if we measure to arbitrary accuracy, we will be able to determine whether the planet went through the left slit or the right slit. And so it shouldn't make an interference pattern. And it's true of planets, but let's just take a molecule, something that has a little bit of mass. If the gravitational field is classical, then we'll be able to determine, at least in principle, which slit it went through, and so we won't get an interference pattern. So that was roughly Feynman's argument. It's maybe refined by Yakir Aronoff, but that's roughly the argument. Are there any questions about that argument? Because it's quite a good, it's a very good argument. No? Okay, so that was the argument, Feynman's argument about why we had to quantize the gravitational field. But let me ask, let's consider the electromagnetic field. Now, if the electron goes on the left or the electron goes on the right, the electromagnetic field will be different, depending on whether the electron goes through the left slit or the right slit. And why is it that we can't measure the electromagnetic field? And so we can measure the electromagnetic field and determine which slit the electron went through, and therefore electrons shouldn't make interference patterns even without gravity. Does anyone know why that? Why we still see interference patterns despite the fact that the electromagnetic field is different depending on whether the electron goes through the left slit or the right slit? Are people could write in the Q&A, or are people able just to somehow raise their hand and answer?
There's a suggestion in the chat that the probability for single photon emission is too small.
So there is the I guess what's something called the far field. So where you're actually emitting photons, and you're detecting photons. But in addition to that, there is also just you don't need to emit photons here to know that the electromagnetic field will be different depending on whether the electron is going through the left or the right. It is, right? I mean, it's just a fact of the matter that if the electron goes to the left versus the right, the electromagnetic field is different, regardless of whether a photon is emitted or not. And so, why is it that we cannot measure this electron? Why can't we use that to determine which slit the photon goes through or the electron goes through?
Another suggestion is that the quantization of electromagnetic waves limits us.
Meaning that it can't emit enough, but that sounds a bit similar, like it can't emit a photon in order to change the electromagnetic field. Is that maybe roughly the argument? And again, there's something called the far field or the near field. And the electron doesn't need to emit photons. It is simply still a fact that the field is going to be different. And so we can measure the electromagnetic field at all these different points in space, and it is different depending on whether the electron is on the left or the right.
Someone else suggested the electromagnetic field is in superposition. And someone else said because we collapse the wave function when we measure it at the slits.
Well, I guess what we're trying to do here is we're trying to not measure at the slits. We're trying to measure, far away. We could measure. I mean, in some sense, we know from quantum information theory that if there's enough information in the slits or in the electromagnetic field, if there's enough information somehow there to determine which slit it went through, then there will be no interference pattern. And so it's a bit of a it may be a bit of an initial puzzle. Why, since we know that the electromagnetic field is distinct depending on which slit this electron went through, you might think, oh, there is enough information in the electromagnetic field to determine exactly which slit the electron went through. And so here we have here's the entangled state I was talking about. So the electron or the planet goes through the left slit or the right slit, and it becomes entangled with the electromagnetic field. So there's the state of the electromagnetic field if the electron goes through the left slit, and there's the state of the, let's ER is the state of the electromagnetic field if the electron went through the right slit. So this looks like it should and I guess the question is, does this decohere the electron so that there's no interference experiment? And if not, why not?
There are some other suggestions in the Q&A
Okay.
part. Someone said it might be because we can't measure the electromagnetic field sufficiently accurately. And someone else said the photon picture only gives a statistical picture. So can we measure the electromagnetic field with just one photon?
Well, I guess we can't measure it with just one photon, but we could imagine that we have an array of detectors everywhere throughout all of space, everywhere, and that we can measure the electromagnetic field everywhere. And I guess the question is that if we were to measure the electromagnetic field everywhere, would we be able to distinguish the these two states of the electromagnetic field? And I think both the previous answers are getting towards the right, are maybe have the right answer or getting at the right answer, which is that in quantum theory, there's a strange, there's this thing that you can have two different states, which are distinct. So, the electric field is different depending on whether the electron went through the left or the right slit. So we have the EL and the ER are different quantum states, but they are not orthogonal to each other. So they have a large overlap, and it's very difficult to determine them apart. You can do it, as I think someone maybe suggested, statistically. If you do this enough times, you could distinguish the left electromagnetic field from the right electromagnetic field. But each time you run the experiment, you only have some probability of learning which one it is, because they are, they're not orthogonal, even though they are different. And this is just like the fact that, they, in some sense, you don't have decoherence here because the electron is not making too much of an imprint into the environment. Here, the electromagnetic field is the environment. It's not making the change that it's making to the environment is making a change to the environment, but it's not enough for us to distinguish what happened. So quantum states have this property that you can have two distinct classical states which have overlap. And Feynman's argument is particular to a classical field, because what you can say is, for classical states, you cannot have different classical states and have them be non-orthogonal. That's at least what he said. So he says that if there are two different the gravitational field will be different depending on whether the atom or the molecule or the planet went through the left slit or the right slit. They'll be different, and classical states of the gravitational field you can tell them apart. There's no such thing as a classical state which is different and still non-orthogonal to these two. Sorry, you can have two classical states which are different and non-orthogonal. Is that argument clear? Any questions about that argument? That's, I think, Feynman's argument in a nutshell. Okay, and so that's so I think the key takeaway here is that we understand why for quantum fields we can still have an interference pattern, because we can have distinct quantum states which are non-orthogonal. But if you have a classical electromagnetic field or a classical gravitational field, you can always tell them apart, and therefore you shouldn't have an interference pattern. And so that's the mystery, or that would be the mystery, or that would be the reason why we should quantize gravity. And there's, of course, a loophole there, and that is that classical states can be different and so they can't be different and non-orthogonal unless they're distributions. In other words, unless they're probabilistic or statistical. So you can imagine maybe that the gravitational field is noisy, it has is a distribution of possible fields. So for example, if the planet goes on the left, there's a statistical process. It interacts stochastically with the gravitational field and only changes it with some probability. And in such a case, you can have the two different states of the gravitational field, depending on whether the planet went through the left slit or the right slit. They will be different, but you can't always tell them apart because the interaction is stochastic, and the states that are produced, depending on whether whether the planet went through the left slit or the right slit, the state that is produced are not orthogonal if the interaction is statistical or stochastic. Okay, so classical gravity is incompatible with quantum theory unless the coupling between matter and gravity is stochastic. All right, and so there you see already that there's this link now with the black hole information property. If we are going to believe that if we're going to posit, just for sake of argument, that gravity is fundamentally classical, then we get for free that there's information destruction, that there is stochastic noise in our theory. So I'll pause there and I'll see if there's any more questions. Do people understand that argument, and do I understand that, why stochasticity is a loophole for that argument? Okay, so that's Feynman's argument and of why we have to quantize gravity, and we see that there is a loophole. And now I want to get at a second popular argument and show you that that argument is based on, I think if you're in quantum information theory, you might see right away what's wrong with it. And the argument, I think, arises because in the gravity community, fairly early on, when people discussed both whether the gravitational field had to be classical, but also how should we somehow, if we want to look at, say, an evaporating black hole or the early universe, cosmology, and we want to treat the gravitational field classically, how should we do it? What they did was they took Einstein's equations, so up here g mu nu equals 8 pi t mu nu, and what they thought we should do is we should take the expectation value. We have an operator which is equal to a C number, and so the way to make this, somehow the way to make this consistent, or the way to deal with the fact that that the matter and t mu nu is quantum, t mu ni I should say is quantum, is to take the expectation value of the right-hand side. So this is called semi-classical gravity, and it's where we take the expectation value of the stress energy tensor, and it's, of course, as we'll see in a moment, it's pathological. It doesn't work as a theory. It's certainly not a fundamental theory, and even to the extent that it gives good answers, the limits in which it gives good answers are, I think, often not that interesting. And let me give the argument about why this theory is pathological. And again, we're going to go to our favorite state, which is this superposition of the coin entangled with the planet being on the left or the right. And let's look at the stress energy tensor of the planet in such a state. If we just look at the planet and not the coin, then if we have a planet on the left with some mass, some large mass m, and a planet on the right with some with probability 1/2, a planet on the right with probability 1/2, then the expectation value of the stress energy tensor is the same as if you have half of a planet on the left and half a planet on the right. Yeah, so on the left-hand side of the slide, we have the situation where we either have a planet on the left or we have a planet on the right, each of which has its ordinary mass. If we take the expectation value, well, that expectation value is the stress energy tensor of half a planet on the left and half a planet on the right, or a planet of half the mass, I should say. So that's the expectation value. And now let's look what happens if we drop a ball, like a test mass, towards the planet. And what we think should happen is what's depicted on the left, that the planet is either on the left, in which case the ball should drop towards the planet on the left, or the planet is on the right, in which case the test particle should drop towards the right. But what happens in semi-classical gravity when we take the expectation value is that the expectation value is 2 half planets sitting on both the left and the right. So you drop the ball and it'll drop towards the center between these 2 planets. And also because you have 2 half planets, they will be attracted to each other and they will start to move towards each other. So in semi-classical gravity, what happens is what's depicted in the right box. And what we believe should happen is on the left. And so classical gravity is bad and cannot be a correct theory, a consistent or a sensible theory which couples, in which we take the classical limit of space-time. And so this was another reason why people assumed that you had to treat the gravitational field quantumly, because their version of what treating the gravitational field classically was this very sick, very pathological semi-classical theory of gravity. Any questions about semi-classical gravity?
We have a question about the previous section, I think.
Okay. Yeah.
The question was, what if you had a gas of molecules going through or a liquid flow of molecules and then measure the gravity? Would interference be more natural?
I'm not entirely sure I understand the question, but if all the atoms are going through the left or the right, so you can either imagine a scenario where you have a bunch of atoms and you shoot them one by one, and they independently decide whether they're going on the left or they independently either go through the left or the right, or a superposition of that. And so, in that sense, it will be very difficult to tell. And we will get an interference pattern because it'll be very difficult to tell which slit these atoms went through. If you put, if they all go, if you have a superposition, so the superposition of them all going through the left or all going through the right is like this cat state that we saw way back at the beginning. I think that's what you're thinking about there. So this is like this state here, where they either are all 0 or all 1. And that, of course, we expect to collapse into one of these 2 states. Either cat is either a 0 or a 1. I don't like to kill cats, so there's 0 or 1s here. And likewise for the gas, if you have many molecules either going to the left or the right, it's like a cat state, and we expect that to be detectable and make enough of an imprint on the gravitational field or even the electromagnetic field that will be able to tell them apart. Does that answer the question, I think? I should say, I think. Does that answer the question?
I think so. Yes. Yeah.
Okay. Okay, and then the third, I didn't put this on the slide, but the third reason that people think that you ought to quantize the gravitational field, or sorry, it shouldn't be why, this is not the reason why you should quantize the gravitational field. This was the reason why we started to quantize, people quantized the electromagnetic field, was because of the ultraviolet catastrophe. That if we have a black body in thermal equilibrium, then the classical theory predicted it should just radiate away, which we don't see. And so this is, the ultraviolet catastrophe. And this was the primary motivation for quantizing the electromagnetic field. But there is not an ultraviolet catastrophe for the gravitational field. Gravity is different. And when people do, there are various back of the envelope calculations that people do. And I wouldn't say there's consensus on this, but the general feeling is there's not an ultraviolet catastrophe for the gravitational field. I think it's a little bit to do with the fact that the density of states is very different. And for example, black holes behave, the heat capacity goes in the opposite direction for gravity, and black holes, there's a natural cutoff in some sense, in that the black holes will form. So there doesn't appear to be an ultraviolet catastrophe, and therefore I would say there's less of a, there's not the same motivation to quantize the gravitational field. All right, so now let me just talk about what the general form of this dynamics is. I think I've just argued that it's possible to have quantum systems coupled to classical systems, that it doesn't contradict a few thought experiments. And we can now have a bit of fun trying to figure out what that dynamics will be. And when I say fun, it's because, I feel a bit, we kind of came in when people had done a lot of fun stuff like, Krauss, you had Krauss looking at completely positive trace preserving maps, and you had Lindblad and various other authors looking at the Lindblad equation and complete positivity and things like this. And we should now look at the same thing here. So we should define what we mean by an object which has both classical degrees of freedom and quantum degrees of freedom, and then ask, how do we mathematically describe this object, and then what kind of dynamics is allowed which preserve the state of the system. So, for example, in quantum theory, quantum states are positive trace one, a matrix in a Hilbert space, so a density matrix. Classical states are a probability density. They're positive and integrate to one. So it's a density over a phase space. And hybrid states are some combination of that. So, for example, let's look at the hybrid qubit. So if you have a quantum qubit in just a pure quantum state, then we represent this by a 2x2 matrix with probabilities P0 and P1. And now if we have a hybrid qubit, it also requires a phase space degree of freedom. So it's like a particle, a classical particle with a Q and a P. And also it has, it's a matrix of, a density matrix. It's not a density matrix in the real sense. So we have the 2x2 matrix, which represents the quantum degrees of freedom, but then we also have a dependence on phase space. And so the quantum part, we would expect it to be trace one, but here it just has to have a positive trace, and it's only when we integrate over phase space that we need to normalize it. So to normalize it, we should trace over the quantum degrees of freedom, integrate over the classical degrees of freedom, and that gives us one. So that's the normalization condition. And then it also has to be a positive, it must be positive. Okay, so that's the hybrid state. It's this classical quantum state. Any questions about that? I'll try and leave some time for questions, so I'll maybe just go on for another 5 minutes. What kind of dynamics is allowed? Well, it has to be linear in, just like in quantum theory, we need to be linear in the density matrix. Here we have to be linear in this CQ state. And that's because effectively the argument that we gave before about this planet being on the left or the right, we imagine flipping a coin and making some entangled state with a planet on the left or the right, conditioned on the coin. And the dynamics, if the dynamics acts on the planet, then the dynamics doesn't know, we could look at the coin and know whether the planet is on the left or the right, and the dynamics shouldn't really know whether we looked at the coin or not. And so we have to be linear in this density matrix. So the dynamics has to be linear. It must preserve the state space. So this is, the condition for the condition for classical theory, quantum theory, and for classical quantum theory, there's like a classical quantum version of the Krauss representation theorem. So we have this positive CQ state. It's normalized in this funny way of integrating and tracing, or here summing, because I've for some reason written a discrete state space. And then we have an equivalent of the Krauss representation theorem here. You can see that it's actually, you have very similar looking conditions, both for classical probability theory, for quantum theory, and for this classical quantum theory. You have very similar looking conditions. And likewise, if we then assume that our dynamics is memoryless, then your fundamental equation looks very similar to the looks similar to the the Lindblad equation or the GKLS equation. So on the top you have the Lindblad equation for quantum theory. The middle line is the I forget now what it's called actually, but it's basically just the law of conditional probabilities. So you have a conditional probability, which a rate equation that tells you how probabilities change and in a way that makes them always positive. And likewise for this classical quantum dynamics, it's been known for a while actually, but I think in an overlooked paper that you can have this CQ dynamics in a very abstract way, which is completely positive trace preserving. Okay, so now this dynamics, which is due, I think, initially due to Blanchard and Jellick, it's very abstract. So this is it here on the bottom in green, and now we want to apply this to a real theory. So, for example, gravity, and there's a lot you need to do in order to do that. This is very abstract. You need to involve some interaction Hamiltonians, et cetera, et cetera. So there's a way of doing that. And various constraints one has. And rather than show you the gravitational theory, which is a little bit complicated, I'll just give you a very simple model of a qubit in a magnetic field, like a Stern-Gerlach. This is what a Stern-Gerlach looks like when the position of the particle is classical, but the value of the qubit is quantum. Here's the master equation at the top there. And you can see, maybe if you are good at reading master equations, that the first term tells you that if the qubit is in the one state, then then this particle should hop to the left. Its momentum should decrease. And if the qubit is in the zero state, then the momentum should increase. And so if you start off in a superposition of being in the 0 and 1 state, then what quickly happens is that this thing will hop to the left in momentum or hop to the right. And so by monitoring the momentum, you know for sure whether this qubit is in a 0 or the 1 state. And so because you can unambiguously determine the state of the qubit from the, after some time at least, from the state of the momentum, the classical degree of freedom, after some time you'll be able, the qubit collapses. You could say that the qubit has collapsed to the 0 or the 1 state. And so you get this discrete jump in momentum and this collapse of the wave function to the 0 or the 1 state. So here we have some time photography. Initially, the qubit is in a superposition and the particle is just sitting in the origin. And after some time, what happens is you get two distinct possibilities. Either the qubit is in the 0 state or the 1 state, and the classical degrees of freedom somehow are measuring this. And so for gravity, this master equation is a very simple one, but for gravity, you effectively can construct something which I call non-commuting Hamiltonian dynamics. You can construct kind of this funny non-commuting Poisson bracket in some sense, which is always positive, which is something that has been, I think, missing in a lot of other master equations or attempts to couple classical and quantum degrees of freedom. And then you go to something called the ADM picture of gravity, the ADM formalism for gravity, and impose some constraints, and you can get some consistent dynamics. Imposing the constraints is I think one of the key outstanding issues. So let me now summarize. I haven't told you anything about the gravitational theory, but that's okay. The main key message is that what I want to say is, let's just assume for the sake of argument that space-time should be treated classically and see where that takes us. And what I claim is that there's very constrained dynamics, you don't have much choice in the kinds of dynamics that's possible, and that dynamics necessarily causes collapse of the wave function, or the the wave function necessarily becomes definite in some way. You necessarily have to have stochasticity and noise, and so there will necessarily there must be information destruction. And there are various ways that I think you could test this, and maybe who knows? I think the smart money is on the fact that we should treat like we must quantize gravity, but here we see it's a possibility that gravity should be it doesn't have to be quantized, and so we could treat it fundamentally. If not, though, it's possible that this is just the classical limit of quantum gravity. And maybe I'll also just say that I think what's maybe interesting here for some people is that there's a lot of places where quantum information becomes very important. So the stronger version of the black hole information problem is a contribution from quantum information theory. Understanding that we should use a master equation rather than semi-classical gravity, I think, comes from having a bit of a quantum information theory background, and we understand well how such master equations, we kind of know how they should behave. And this idea of looking at some of our cherished theorems, like the Krauss representation theorem, but generalizing them to this classical quantum picture, I think is some other contributions that you can make coming from quantum information theory. So there's a lot that quantum information theory can tell us, I think, about gravity, or about at least this effective theory of information destruction. And with that, I'll thank you for your attention.
Thanks a lot for the talk. That was really interesting. I think you managed to cover a huge number of different aspects of this, of the various issues about classical and quantum gravity. So yeah, if anyone has any questions, please put them in the Q&A section. We have one already, which is, how does this address the singularities that appear in black holes as a consequence of classical gravity? Singularities are unphysical, and do we not need a theory that can resolve the singularities?
Yeah, that's a good question, and I don't know how it would resolve the singularity, but I do know that it can. So if you have a probably distribution, you just have a different set of equations for the state of the field, and so at the moment we're not able to solve them. So I don't have any strong words to say, except just to say, yeah, that I guess it's a hope more than something which I am able to say that it achieves.
Okay, we have another question in the chat. So the question is about what you regard as a fundamental piece of information which is transmitted. So I guess that might be in the context of the black hole information paradox, possibly.
Sorry, can you repeat the question?
What do you regard as a fundamental piece of information which is transmitted?
Can that person clarify whether it's, are we talking about the black hole information problem here, or?
Maybe the person that asked the question could clarify in the chat.
Yeah. I mean, in some sense, when people talk about information destruction, it's you can just think of it as you have a pure state going to a mixed state. So in black holes, we have pure states going to mixed states, and in that sense, there's information destruction. And it's not really that important what that information means, other than the fact that we had some initial state of our system, and we no longer, we're now in a mixed state, so we can no longer recover with certainty what that initial state was. So that's the information that is lost in that sense. It's just the initial what was the initial state of our system. In these classical quantum theories, there's in some sense it's the there's the information destruction is happening just because there's stochastic coupling between the quantum system and how it affects the gravitational field. So that's just a, I wouldn't say there's in some sense, in a deterministic theory, you would know exactly which slit it went through, I guess is one way to think of it. And the information that's being destroyed is which slit it went through. But that's just a particular example.
Thanks. And we have a couple more questions in the Q&A. One of them is, can a classical stochastic process coexist with Lorentz invariance?
Great question. Who asked that?
They're anonymous, so we don't know.
They're anonymous. So the answer is yes, there are. So, so for example, if for a Lindblad, if you're familiar with the Lindblad equation, then if I take the Lindblad operators in say a scalar field to be phi, to be diagonal phi, then that's a local theory which is Lorentz invariant. So that kind of that's an example of a stochastic theory which is Lorentz invariant. But it's slightly tricky. There are other theories which appear, which sometimes are called Lorentz covariant, which turn out not to be Lorentz invariant.
Okay, thanks. We have another question. What happens if you purify all the classical degrees of freedom into one larger quantum system? Would that be a quantum theory of gravity?
Good. So that's a great question as well. And the so one of the reasons why people think that information is preserved in black holes, for example, is that, as you say, well, we could always just go to the Church of the Larger Hilbert Space. That's why I'm in the Church at the moment. Because I like the Church of the Larger Hilbert Space, we can always imagine that our theory with information loss is a unitary theory that exists in some larger Hilbert space. So we can always imagine that that there is some larger extra degrees of freedom that we're not taking into account, and if we took those extra degrees of freedom into account, then the evolution would be unitary. And so that's, I think, a reason why why people think that there ought to be a unitary theory somewhere there. But what's interesting is that these classical quantum theories don't necessarily have a purification. You can't always go to the Church of the Larger Hilbert Space if your theory is one of these hybrid classical quantum theories. And the reason is that, in some sense, the constraints on positivity are much weaker, because you only need to be completely positive trace preserving in a particular basis, in some sense you can think of it, of your classical system. And so there's not necessarily a purification of these theories. And so in some sense you get around that objection. There's a few other objections that people have had to either classical theory, treating the gravitational field classically, or why we believe that information loss, why our fundamental theory should be unitary. And this theory gets around a few of them, I guess.
Great, thanks. We have a couple more questions. One is, what kind of experiments would be needed to test these semi-classical theories?
So one of the things which you see here is that positivity places some constraint, quite a big constraint. And so if there's this trade-off which happens between how much decoherence you have and how much in the quantum system, and how much dispersion or diffusion there is, I should say, in the classical degree of freedom. So what can happen is that you have something has to give in some. So both things can't be small, which means that you can measure. There's something there to be measured and to detect. So either there will be if it's in this case of the gravitational field, either there will be some diffusion in the gravitational field, or there will be very fast decoherence. Now we know that there's limits on how quick massive objects decohere. We're pushing those limits all the time. Maybe we'll push them. Maybe there is no limit. But if we believe there's a limit, then somehow there is. We don't have a lot of. We see that we can have long coherence times, and that means that there must be a lot of diffusion in the gravitational field. So that's one signature of this theory.
Great, thanks. Another question is, could you clarify again what you mean by a hybrid system? And I think that relates to someone else's question, which is a classical quantum system. They said they're puzzled by that. So I think they're similar.
Okay. Yeah, sorry. I maybe am using language that's not, an apology if I'm using language which is unfamiliar. So I guess I think I have phrased it in different ways, which is probably why there's some confusion. So you can think of that I have two systems, one which I treat classically and one which I treat quantumly. So for example, a qubit coupled to a classical particle. But you can also just think of it as one hybrid system. It's a qubit with a position and a momentum, and so it's a hybrid qubit. It has a spin, or it's a 0 and 1, which is living in the Hilbert space, and then it has a Q and a P, which lives in phase space. So it lives both in Hilbert and phase space. So you can think of this. You can think of the state space as being that at each point in phase space, I have a. Let me share the screen again. At each point in phase space, I have a Hilbert space. And so you can think of it either as two separate systems, one which is classical, one which is quantum, or you can think of it as a hybrid system which has both quantum degrees of freedom and classical degrees of freedom. Did that answer the question?
I think it did, yeah. Yeah, and the anonymous person that asked it does as well.
Okay.
We have a couple more questions if you still have time, but we can.
Yeah, I'm happy to. I guess the nice thing about online presentations is people can leave whenever they want to without.
Yeah.
Without feeling like they're being rude.
Yeah. One question we have is, does the use of master equations necessarily mean that we are only dealing with open systems? Does this preclude the theory from being fundamental?
Right, so this is this question of whether we should treat this theory as fundamental or is this an effective theory? And I think if you believe in unitarity, so I think it's a bit related to the previous question. Can't we always just imagine there's an environment there, and therefore why not just treat it as a non-fundamental theory where there is this environment? And so I think if in the purely quantum case that's true, but in the classical quantum case you can't always purify it. And so in the case of this classical quantum coupling, because you can't always consider that it's part of that there's an environment which we're not observing, and it's the interaction with the environment that is causing this interaction, then you would have to regard it as fundamental. But I'm not wedded to that interpretation necessarily. I think we have a need to understand the classical limit of, say, when we take the classical limit of the black hole, and so it's interesting just to understand this as an effective theory.
Great, thanks. The next question is, if we talk about information creation and destruction, what would you say about vacuum fluctuations? If it's just preserving information, does it mean that there is some information encoded in the background?
I'm not sure I understand the question entirely, but there are I mean, the vacuum, as you've said, the vacuum, there's all these vacuum fluctuations. In some sense, though, that state is pure. So the Minkowski, the Minkowski vacuum, if we're living in Minkowski space, let's assume that for the moment, there's vacuum fluctuations, but the state itself, the Minkowski vacuum, is a pure state. If we perform local measurements, and also measurements which are local in time, in other words, we turn on and off our detector, we will detect particles. But that doesn't, that's just because we made a particular kind of measurement. We could imagine someone with a measuring device as large as the universe, and then they would see that the universe was in a pure state. So in that sense, all the information is there. It's just that we're not necessarily able to access it very well because we don't have a measuring apparatus the size of the universe. I don't know if that answers the question or not.
Yeah, I think so. And we have, I think, the last question, which says, you were mentioning about non-commutative algebra. Do you mean non-commutative in space-time level?
No, I guess what so there's many different words that people use. So I could write it because it's maybe kind of interesting. Maybe I'll do that. And this is maybe a bit too, maybe people will leave when I do this. It's probably a sensible thing to do. Let me share the screen here. I guess what I meant is, do people see this thing here?
Yeah.
Okay. So it's like a pad of paper, is that right?
Yeah, that's right.
Okay. And I guess in phase space and in gravity, for example, everything looks like a the evolution is given by usually it's like you have the Hamiltonian vector field, and then it's that's what the evolution law looks like. So you have a divergence in Q and P, and the direction of that divergence is coupled with some Hamiltonian vector field. And what I just mean is that you can make this, you can think of this in some ways as maybe being something like this divergence. If I want to think of a divergence, a discrete divergence, I can think of something that looks like Q plus delta. So this is just the divergence in Q minus rho of Q over delta. So that's a divergence. And then I want to make a non-commuting version, and it looks something like this. L with Lindblad operators, L rho Q plus delta L minus, and then here we have an anti-commutator. You'll notice that this looks like very much like a Lindblad equation in some sense. So if there was no delta here, this would look like a Lindblad equation because we have the sandwich. If people recognize this is the sandwich term from a Lindblad equation, and this is the anti-commutator from a Lindblad equation. But here it looks very much like, in some sense, a divergence. And so this is the kind of thing we do in order to take this master equation and get something which this term arises naturally. This kind of it's non-commuting in a funny way, isn't it? But it's a kind of a non-commuting divergence. This would be the commuting version, and so it's this non-commuting divergence, and it somehow arises naturally in these theories and gives you the dynamics.
Thanks. Thank you for going through that. I think that's all our questions.
Yeah, that probably killed any further questions.
I'm sure that someone has also asked if the slides are available.
I'm happy to send that to you if you want to post it on Facebook or whatever.
yeah, we can do that if you send them to us or to someone on the committee afterwards.
Sure.
Yeah. Yeah, brilliant. I think definitely there's loads that we could discuss about this, but we should draw things to a close in the interest of time. Thanks again for the talk. That was really, really interesting. And I think you've given everyone lots to think about. And the talk is recorded, so people will be able to watch it afterwards as well. Yeah, and everyone who is still here, please come along to the next few events of Quantum Information Society. We've got Denise Ruffner, the Chief Business Officer of Cambridge Quantum Computing, doing a Q&A session next Monday. So please come along to that. And yeah, look forward to hopefully talking to you another time as well. So
Great.
thanks a lot for coming
Thanks
today.
very much, Maria. Thanks very much. And thanks everyone for listening.
Thanks to everyone who got involved with answering the questions during the talk as well. Okay, see you.
Bye.
Bye.